Well, hello there. Mr. Sutton here, bringing you the AB Calculus 513 Extra Practice number 2 solutions on average value. On this problem, we want the average value of this polynomial from -1 to 3. So setting up our average value integral, we're going to have 1 over 3 minus -1, that's b minus a, times the integral from -1 to 3 of this polynomial. So that's going to be 1/4 times, this bumps up to a 4, divide by 4, you've got -1/4 x to the 4th. And then this will bump up to a 3, dividing by that we've got minus x cubed. And again, we're going from -1 to 3. So I'm going to leave this 1/4 out here, and inside a big parentheses, we're going to do all this stuff with 3 plugged in, minus all the stuff with -1 plugged in. And it's free response, so you could leave it like that, or you could simplify it. If we do go ahead and simplify it, this is going to be -81/4 minus 27, and we still have that 1/4 out there. Over here, this is going to be, let's see, minus, so that's a plus 1/4, and this is a -1 to the 4th, so that's not going to change anything. And then over here we have minus makes this a plus, but then you have a negative to the 3rd, so that's -1 when all is said and done. Adding some things together in here, let's see, -81 and 1 over 4, that's -80 over 4, which is -20, and we still have that 1/4 out there. And then -27 minus 1, that's -28. So this is 1/4 of -48, which is -12. On this problem, we want the average value of this piecewise function on the interval from 1 to 4. So to do this, let me first set up my average value fraction. I'm going to have 1 over b minus a, or 1 over 4 minus 1. And then I need the integral. Normally I would have the integral from 1 to 4 of a function, but this is a piecewise function, so I'm going to have to split it up. So I have the integral from 1 to just 2 of my first rule, 2x minus 4 dx, plus the integral from 2 to 4 of the second rule, this x squared piece here with a dx next to it. And at this point, I'm just going to plug it in the calculator because this is a calculator question. So just to show you what I've got so far, I've got 1 over 4 minus 1. I guess I could have said 1 over 3. Here's my first integral from 1 to 2 of the 2x minus 4 function. Now I'm going to add to that, and I'm going to do math 9 here. The integral from 2 to 4 of, and then I'm going to enter this polynomial. So we have x squared minus 6x plus 8, and then I'll put a dx over here, close the big parentheses, and all of that craziness comes out to -0.778. For this problem, we're told that big and little f are differentiable functions, and big F is the integral of little f. And we also have two values for big F. At a and b, they're both values of -2. And they're telling us a is less than b. So which is going to be true? So this is a good one for process of elimination. If you look at choice A, f of x equals 0 for some x between a and b, well, I mean, maybe that's true. It's kind of hard to tell based off what we had here, but I don't know that we can eliminate this right off the bat. The next one, f is greater than 0 for all x between a and b. So this one makes a little bit less sense. F is the instantaneous rate of change, the slope of big F. And here they're telling us between a and b, we're going from a y value of -2 to a y value of -2. That doesn't seem to imply that your slope has to be positive, at least not positive for all x's. So I would say b can be eliminated for that reason. And really, c can be eliminated for the same reason. If you're starting and ending at the same y value, why would you conclude that you're increasing or decreasing for the whole interval? It makes no sense. So now let's take a look at d and e. D, they're saying that the value of f is less than or equal to 0 for all x between a and b. And I'm not really sure we can conclude that. I mean, we're starting and ending at negative values, but how do we know that we don't spike up to some really positive values in between and pick up a lot of positive area? We don't. So I don't think we can conclude D either. E, f of x equals 0, for some x between a and b? Well, this one doesn't really seem likely either. If you're starting and ending in a negative number, it's at least possible that you stayed negative for the entire interval from a to b, in which case there's no way you're going to have an area of 0. So by process of elimination, choice A is looking pretty good. Now here's how you could actually prove choice A. This is talking about a specific value of the derivative of big F. And when we're trying to guarantee that we're going to get a certain value for a derivative, we're usually talking about the mean value theorem, which says that the a-rock from F has to equal the i-rock at little f at some value. So let's find the average rate of change of big F and see what we come up with. So we can find the average rate of change between A and B by doing big F of B minus big F of A over B minus A. Now we don't know what B and A are. However, we do know that big F of A and big F of B, both of these are both negative 2's. It's the same number. You're subtracting a number from itself. So this is going to be 0 in the numerator. We know the denominator is not 0. They said here that A was less than B. I mean, at the very least, they're not the same number. So this is going to be 0 over not 0, which comes out to 0. And that means we are guaranteed that the instant rate of change of big F, little f, has to equal 0 somewhere on the interval from A to B because of your mean value theorem. We're further guaranteed this because they said that big F was differentiable, so the mean value theorem will apply here. So for this reason, or process of elimination, we can pick choice A. For this problem, we're given a first derivative of 1 over x, and they're asking for the average rate of change of y with respect to x on the closed interval. So if we're asking for the average rate of change of some function, and we don't know what the function is, but we know what its instantaneous rate of change is, we're essentially asking for the average value of the rate of change of the derivative. So we're going to find average value for this derivative function here. That's going to be 1 over 4 minus 1, that's b minus a, times the integral from 1 to 4 of this function, 1 over x dx. So that's 1/3 times, and now the antiderivative of this is ln of absolute value of x from 1 to 4. We don't actually need the absolute value here because we're guaranteed to be plugging in positive x values, but I'll leave it in there temporarily. So this is 1/3 times ln of 4 minus ln of 1. That doesn't match any of the answer choices, but we know that the ln of 1 is 0 because you're asking what do I have to raise e to in order to get 1? Well, you can raise anything to 0 to get 1. So that's just going to go away then. We have 1/3 times the ln of 4. And that still doesn't match any answer choices. What did we do wrong? So this is where they were kind of sneaky with log rules. You could rewrite 4 as 2 squared. And part of the tip-off that you needed to do this, if you look at the answer choices, I mean, we have 2 answer choices that have ln's, and they're both ln's of 2. So clearly, whatever this comes out to, we need to express it with ln of 2. And the only way to do that is by turning 4 into some power of 2. All right, so we've done that. We know with logs, if we have an exponent inside, we can pop that out as a multiplier. So this is really going to be 2/3 ln of 2. And that finally matches an answer choice, choice C. For this problem, if f is continuous on a closed interval a to b, then there exists C such that C between a and b, and the interval, the integral from a to b of f of x equals, and then they just expect you to fill in the blank. All right, so what's going on here, you've got continuity on an interval, and you've got some value, and we're talking about integrals. This sounds kind of like the mean value theorem for integrals. Recall that if we have continuity, then we're guaranteed that there's some c value such that f of c equals the average rate of change of the function. So 1 over b minus a times integral from a to b of f of x dx. So this is our mean value theorem for integrals that I just talked about. So how do we turn that into something that's going to help us here? Well, they want us to tell them what integral from a to b of f of x equals. We have that in here. This is actually an equation with the integral that we want to isolate in here. And if you look at some of the answer choices, I mean, we're on the right track here. It's all A's, B's, and C's. So to get this integral by itself, we can just multiply both sides by b minus a. That'll give us f of c times parentheses b minus a. And we've just filled in the blank here. We just have to look for f of c times b minus a in the answer choices. And that's going to give us answer choice E. So this was all about writing the mean value theorem for integrals and then just rearranging it to give you what you wanted. On this problem, f's a twice differentiable function, and f of 1 is 2, f of 3 is 7. We want to know what's true for the function f on the interval from 1 to 3. So option 1, average rate of change is 5 over 2. Well, that's pretty easy to check. Let's just use AROC here. We've got 7 minus 2 over 3 minus 1. So that's going to be 5 over 2, which is exactly what they said, so that's true. So anything that doesn't have 1 in it down here has to go. Choice A is gone, choice C is gone, and choice E is going to be gone, so it's really down to B or D. Now, if you've done this elimination game already, you notice that 2 can't be one of the choices based off of the 2 options left. So you could just ignore 2 and move on. But if you were wondering why 2 doesn't work, they're asking about the average value of f, which means you would need to take the integral of f, and there's no way to do that based on the information they've given us. Since we need to integrate, we don't really know anything about the average value of f. All right, so moving on now, the average value of f prime is 5 over 2. Well, the average value of f prime is the rate of change of f. So the average value of f's rate of change is literally going to be the average rate of change of the f function, which we just found to be 5 over 2. So since this is the average rate of change of f, just a different way of saying it, this is also going to be true. So then choice D, options 1 and 3, is what makes sense here. For this fun problem, we want to know the average value for y for the part of this curve here that's in the first quadrant. So this is a multi-step problem. First off, we have to figure out on what intervals this function is in the first quadrant, and then based off of that, we can try to find the average value of that part of the curve. So first, we're going to set this equal to 0, and I can factor out an x here. That leaves me with 3 minus x. That means I have values of 0 and 3 that I'm going to test out on my number line here. So 0 and 3, these are border values. I'm going to do some sign analysis around these now to see where I have positive y values. Because if I want the first quadrant, at the very least, the y values need to be positive. So if I plug in a number less than 0, like -1, that's going to give me a negative and a positive, which comes out negative. If I plug in 1 here, that's going to give me a positive, so positive. Plugging in a number bigger than 3, that's a positive and a negative, so negative. So I see here that I have an interval that's positive for y values between 0 and 3. And since the x values are positive between 0 and 3, that means 0 to 3 is our quadrant 1 interval that we're going to be using to find the average change, or the average value rather, for this y function. All right, so setting up our average value, we have 1 over 3 minus 0, this is b minus a, times the integral from 0 to 3 of, and now this 3x minus x squared function. So this is kind of kicking us when we're down. We already had to do this work to find this 0 to 3 interval. Now we have to do more work without a calculator to evaluate it. Woe is us. But let's keep going. So we have a 1/3 there. And now this bumps up to a 2. Dividing by 2, I have 3 halves x squared. I'm taking the antiderivative now. Then this next one, this is going to be minus 1/3 x to the third, evaluating from 0 to 3. And to make my life a little bit easier so that I have less fractions to deal with, I'm actually going to distribute this 1/3 right away. So I'm going to rewrite this as 1/2, because these 3's cancel, 1/2 x squared minus 1/9 x cubed from 0 to 3. All right, now I'm going to take 3 and plug it into these two x's here. And from that, I'm going to subtract all of this stuff with 0 plugged in. And we get our first break here, because all this stuff with zeros is going to get zeroed out and go away. So we're really just looking at this first set of brackets. So this is going to be 9 over 2 minus, let's see, 27 over 9 is 3. This is 9 halves minus 6 halves, which is 3 halves. And that gives us choice C. On this problem, if f is this weird sine-ish function, we want the average value of f on the interval from 0 to 6. Fortunately, this is a calculator problem, so we just need to set up the integral and plug it in the calculator. Average value is going to be 1 over b minus a, so 6 minus 0 in this case, times the integral from 0 to 6 of the f function, which I'm not going to bother rewriting because I'm going to have to plug it in my calculator anyway, and they named it for us. So let's do the calculator now. So this one's kind of a pain to plug in the calculator. I did my fancy fraction in the beginning for the 1 over 6, math 9 to get my integral from 0 to 6, and in here now, you got to be careful. We have a parentheses around the x plus 2 times sine, and then I have to open a parentheses, put a square root in there, and it looks like I've got an extra parentheses in that square root, so I'll get rid of that. I need the parentheses actually around the whole square root to put it inside the sine function. Don't forget to actually put a dx there. And if you've done all that, you should get about 3.348, which fortunately is one of the answer choices, B. For this problem, I've got hot water dripping through a coffee maker, filling a large cup with coffee. Amount of coffee in the cup is given by differentiable function c, and we've got some sample values of c in this table up here. So using a midpoint sum with 3 subintervals of equal length, we want to approximate the value of 1/6 integral from 0 to 6 of c of t dt, and then explain what this means. So we're basically finding the average value, and we'll talk about that later. But let's first find the approximation that they wanted. So we have, I'm going to write this approximately equals, and I need the squiggly here because it's an estimate, it's not the true value. Approximately equals 1 over 6, that's this 1 over 6, times, and now in a big parentheses, I'm going to put a bunch of base times height rectangle kind of area additions in here. All right, so my first rectangle, since this is a midpoint sum, I need to use all the midpoint values. I've got 3 intervals here from 0 to 2, 2 to 4, and 4 to 6. So for my first one, I have to use the y value at 1, because that's the midpoint of that first interval. So I'm going to be doing a base of 2 times a height of 5.3. Next, I'm going to have to use the value at 3, which is the midpoint of 2 and 4. So a base of 2 times a height of 11.2. And then I'm going to use 5, so a base of 2 times a height of 13.8. It's a calculator problem, so I'm going to do this out in a sec. Oh, wait, nope, JK, not a calculator problem. I just remembered this is a no calculator part of the AP. So we've got, you either have to do this by hand, which I'm going to do in a sec, or just leave it the way it is and put the units on it. The units in this case would be ounces, but you would have to understand what this actually was representing to know that. So let me just simplify this just for the heck of it here. So I can actually take this 2 that's being multiplied by all of them and factor it out to go with the 1/6. So that's really a 1/3. And then inside I'm just adding 5.3, 11.2, and 13.8. 11.2 and 13.8 adds up to 25, plus a 5.3 is 30.3, and a third of that is just going to be 10.1. So I didn't need to simplify it, but I did. So what does this mean? So right here, this is giving us the average amount of coffee in our cup, and we're going to have to add a few things here. So this is the average amount of coffee in a cup. What's the units on this? This is in ounces from 0 to 6 minutes. And I didn't put ounces up here, so I'm going to put it down here. So the average amount of coffee in the cup from 0 to 6 minutes is 10.1 ounces. There we go. We've got the units, we've got the amount, we've got the average, what it is, and we've got the time here.